What is external device? By definition, it is an external device that attached to the computer by a link to an I/O module. The link is used to exchange control, status, and data between the I/O module and the external device. External device is also known as peripheral. There are three categories of external device. The first one is human readable, for communicating with the computer user such as monitor, printer, or speaker. Next up is machine readable, for communicating with equipment. And finally, communication for communicating with remote device. The interface to the I/O module is in the form of control, data, and status signals. Control signals determine the function that the device will perform. For example, send data to the I/O module using input or read. Accept data from the I/O module using output or write. Report status or perform some control function particular to the device. Control logic controls the device operation in response to direction from the I/O module. The transducer converts data from electrical to other form of energy during output and from other form to electrical during input. Buffer is associated with the transducer to temporarily hold data being transferred between the I/O module and the external environment.
Finally, we have interrupt-driven I/O. Interrupt-driven I/O is when processor issues an I/O command, continues to execute other instructions, and is interrupted by the I/O module when the latter has completed its work. It overcomes CPU waiting, which means no repeated CPU check-in of device. It also allows I/O module interrupts when it is ready to interrupt. Let us consider the role of the processor in interrupt-driven I/O in more detail. When an I/O device completes an I/O operation, the following sequence of hardware events occurs. The device issues an interrupt signal to the processor. The processor finishes execution of the current instruction before responding to the interrupt. The processor tests for an interrupt, determines that there is one, and sends an acknowledgement signal to the device that issued the interrupt. The acknowledgement allows the device to remove its interrupt signal. The processor now needs to prepare to transfer control to the interrupt routine. To begin, it needs to save information needed to resume the current program at the point of interrupt. The minimum information required is the status of the processor, which is contained in a register called the program status word (PSW), and the location of the next instruction to be executed, which is contained in the program counter. This can be pushed onto the system control stack. The processor now loads the program counter with the entry location of the interrupt handling program that will respond to the interrupt. Depending on the computer architecture and operating system design, there may be a single program, one program for each type of interrupt, or one program for each device and each type of interrupt. If there is more than one interrupt handling routine, so what processor can do? The processor must determine which one to invoke. This information may have been included in the original interrupt signal, or the processor may have to issue a request to the device that issued the interrupt to get a response that contains the needed information. Once the program counter has been loaded, the processor proceeds to the next instruction cycle, which begins with an instruction fetch. Because the instruction fetch is determined by the contents of the program counter, the result is that control is transferred to the interrupt handler program.
At this point, the program counter and PSW relating to the interrupted program have been saved on the system stack. However, there is other information that is considered part of the state of the executing program. In particular, the contents of the processor registers needs to be saved because these registers may be used by the interrupt handler. So, all of these values plus any other state information need to be saved. Typically, the interrupt handler will begin by saving the contents of all registers on the stack. The interrupt handler next processes the interrupt. This includes an examination of status information relating to the I/O operation or other event that cause an interrupt. It may also involve sending additional commands or acknowledgements to the I/O device. When interrupt processing is complete, the saved register values are retrieved from the stack and restored to the registers. The final act is to restore the PSW and program counter values from the stack. As a result, the next instruction to be executed will be from the previously interrupted program.